Hello, everyone. My name is Kevin Satzinger. I am a researcher at Google Quantum AI, and today I am excited to share with you some of our progress in superconducting quantum computing. And this is kind of the home movies version of a presentation I've given at a couple of recent in-person conferences, my first in-person conferences since the before times. But let's get started. This presentation will cover 4 parts. First, I will describe Google's path to an error-corrected quantum computer, then how our qubits work, and finally, I want to describe 2 recent papers that have come out of our group about topological quantum states and error correction. So let's get started. This is a photograph that I took recently nearby on a bike ride in Santa Barbara. It's the view from La Cumbre Peak, which is about as high up as you can get in the Santa Barbara area without the benefit of a flying machine. And I thought that such a big picture was appropriate given this subject matter, which is to describe our grand plans to build an error-corrected quantum computer. And building such a device is a really significant undertaking. And so we've kind of broken it up into a sequence of milestones to help us chart our progress and align our efforts along the way. And the next milestone that we are planning is a logical qubit prototype, which will then follow up with a logical qubit with algorithmically relevant logical error rates. And I'll elaborate more on those 2 milestones in a minute. Once we've accomplished that, it's really a matter of scaling up at a significant level. And our plan is to make a modular architecture where we have kind of a tileable module that contains perhaps 10 logical qubits on it. And then we can connect together in larger and larger assemblies, not just the qubits themselves, but also the supporting packaging, the wiring and cryogenics, the electronics and software and so forth. And if we can operate at a large enough scale, we would then realize the error-corrected quantum computer of our dreams. And all along the while, we're going to explore near-term applications with the hardware that we're developing as we make it bigger and better each step of the way. Now, I was talking a lot about error correction there, and I want to provide a little bit of context for why. The reason is that the algorithms that we dream of running on our quantum computer actually require very low logical error rates of perhaps a probability of 10 to the minus 10 or 10 to the minus 12 of an error associated with each operation. And that is a far cry from our current best hardware, which has perhaps 10 to the minus 3 probability of an error associated with each physical operation. So there's sort of this chasm of many orders of magnitude in error, and quantum error correction is the bridge that we hope will help us span that chasm. Now, the idea is to distribute the quantum information across an array of physical qubits to create a logical qubit. And this picture in the middle is an example of a surface code logical qubit where we have this 5 by 5 array of blue qubits that are holding on to our quantum information for one logical qubit. And by distributing the information like that, we make it kind of immune to local issues. And that's something that we'll explore more later in this presentation. But it does come at a cost, not just in the overhead that we're using more qubits, but also in the fact that we do a lot of extra operations in order to measure and find where errors might be occurring so that we can deal with them. And that extra overhead means that making logical qubits like this is only worthwhile if all of those operations are performing really well. And in particular, there's kind of a break-even point where you're sort of barely treading water. And this is related to the concept of the threshold, which we can understand through this expression at the bottom of the slide, where the error per logical gate is proportional to this expression, this ratio of the error per physical gate to an error correction threshold, this kind of break-even point, raised to a power in the code distance, basically the size of the code. So if this quantity in green, 1 over lambda, is small, then as we increase the code distance, we will exponentially reduce the logical error. And an exponential reduction is exactly what we need to cross that chasm of perhaps 7 or more orders of magnitude in error. This quantity 1 over lambda also has significant implications for the overhead, because if you have 1 over lambda that is very small, then you don't need as large of a code distance to get a very small logical error. And we can explore that with this graph on the right-hand side of the slide. Suppose we want the right side of that expression to be 10 to the minus 12. We have an error suppression, a factor of 10 to the minus 12. Then as a function of this quantity 1 over lambda, we can easily calculate how many physical qubits do we need in order to achieve that error suppression. And if lambda equals 1, we're right at threshold, this break-even point, and this quantity diverges. No matter how many physical qubits you throw at it, it's not going to help. But as the error decreases and 1 over lambda decreases, you can see that the number of physical qubits also decreases dramatically. And the particular level that we're targeting right now, which is a good balance between performance and scale, is lambda equals 10, which would require about 1,000 physical qubits in order to realize this level of error suppression. So now that we have a bit more context about the surface code logical qubits that we're planning on using and why quantum error correction is important, I can elaborate a bit on the next couple of milestones. So the first is this logical qubit prototype. And the basic experiment that we want to do is to create a distance 3 logical qubit and a distance 5 logical qubit and compare their performance. And the success criteria is basically bigger is better. The distance 5 qubit, it does better than the distance 3 qubit. And that would be this quantity lambda 3 divided by 5, which is the error per round for distance 3 divided by the error per round for distance 5, exceeding 1. And this is pretty challenging. Even making this a little bit better than 1 would be a significant improvement over any published work in quantum error correction, because you really have to be performing at a very, very high level in order for all of this error correction overhead not to hurt you. And I have to mention here that there have been quite a few recent very cool experiments from related groups running distance 3 codes, both the surface code and related codes, and using superconducting systems and other systems. And you should really check out these works if you're interested in these quantum error correction experiments. They're really cool. And I want to say congratulations to all the people who worked on there. I would also say, I don't know if I mentioned before, that Santa Barbara is a really nice place to live. And I have one more comment about this, which is in these distance 3 works, often there is a comparison between the distance 3 logical qubit and the constituent physical qubits. And sometimes this even comes out in terms of a criticism, where there's a comparison between the coherence time or lifetime of an individual physical qubit and the logical lifetime of the logical qubit. But I wanted to mention that I don't mind at all if your distance 3 logical qubit doesn't live as long as a physical qubit. I don't think that's important. What is important to me is how the logical performance scales as you increase the size of the code. And that's why we're really caring about this bigger is better comparison between distance 5 and distance 3. And to elaborate on why that's the case, consider the rosy scenario where we've managed to build a beautiful, giant error-corrected quantum computer with lambda equals 10, and we have this big logical qubit with 1,000 qubits and 10 to the minus 12 logical error. Depending on the details of how all the errors shake out, it is quite conceivable that you could build a distance 3 logical qubit out of the same stuff and have its performance not be better than the constituent physical qubits in terms of lifetime. So that comparison to me isn't very meaningful. And what I'm more excited about is comparing a distance 3 logical qubit to a distance 5 logical qubit. But of course, even if we manage to get this to work and we manage to get lambda 3.5 just to exceed 1, that's not the end of the road at all, because we need significant performance and scale improvements, about an order of magnitude in each of those, in order to reach this logical qubit milestone on the right. So there's a lot of very exciting and cool work to do in order to make these logical qubit milestones a reality. But that's enough high-level talk. What I want to do now is zoom in by like a factor of 1 billion and tell you a bit about how our qubits actually work. And this is an electron microscope picture that I actually took in graduate school of a Josephson junction. And the Josephson junction is really the key circuit element underlying our superconducting qubits. And the basic idea is to have 2 superconductors that have a weak connection between them. And in our case, it involves a very thin layer, nanometer scale thick layer of aluminum oxide separating two pieces of aluminum. And that creates a Josephson junction where there can be quantum tunneling of Cooper pairs across the junction, and hence there's a relationship between the voltage and current across that junction and the superconducting phase difference across the junction. And that relationship is summarized by Josephson's laws here. And one consequence of those relations is that there's an inductance. This Josephson junction acts like a nonlinear inductor. That is, it has this response to changes in current, and the value of the inductance depends on the amount of current that is flowing through the junction. And that's really a key property that we're going to use in order to make a qubit. And the particular qubit that we're focusing on is the transmon qubit, which is by far the most popular and widespread superconducting qubit. This is basically a nonlinear superconducting oscillator where you take a standard inductor capacitor oscillator and you replace the inductor with these Josephson junctions, which act as a nonlinear inductor. The nonlinearity is important because it causes the energy levels of the oscillator to be unevenly spaced, and so we can directly address the lowest two states and use that as our qubit. The picture on the right shows an example of a transmon qubit. There's a capacitance between the central island in blue and the surrounding ground plane. And the central island is also connected to the ground plane through two Josephson junctions in parallel. And it's two Josephson junctions because this creates a DC squid where we can tune the frequency of the qubit by changing the magnetic flux through that loop. And we can also drive and measure the qubit, as I will discuss more in a minute. Now, there are various imperfections to deal with in a transmon, things like energy loss, dephasing, control error, and leakage into non-computational states. And these kinds of errors are exactly the kind of thing that we need to mitigate with quantum error correction. But let's do a few operations, a few experiments with our transmon. Let's do Rabi oscillations first. This is kind of hello world for a qubit. And here we are sending in an AC voltage pulse through this line on the right side of the slide. This is connected through a coaxial cable up to some electronics that can create a voltage pulse. And the frequency of that pulse is around 6 gigahertz, and it's selected to line up with the resonance frequency of the qubit so that it can drive energy into the qubit and excite it from the 0 state up into the 1 state. And as we drive, we increase this readout signal. I'll elaborate on what this readout signal actually means until we reach this apex here. And that's actually where we have switched between 0 and 1. And we've now changed into the 1 state. And this operation is also known as a pi pulse or an X gate if we send in this particular microwave pulse. An interesting thing about a qubit, though, is if it's in its excited state and you continue to drive it, it actually takes energy back out and takes you back to the ground state, and you oscillate back and forth, and this is called Rabi oscillations. I'll also briefly describe how our measurement works. We use a linear resonator as an intermediary between the qubit and the outside world. Here, the outside world is represented by this transmission line at the top. And we can send in a microwave signal near the resonance frequency of the resonator and then measure what comes out in amplitude and phase. Now, it turns out that the resonance frequency of this resonator actually depends on the state of the qubit. And one way to understand that is if the qubit is in the 1 state, there's a different amount of current that's flowing through its Josephson junctions. So their inductance is slightly different. And that inductance is weakly coupled to the resonator, so it will slightly pull the resonance frequency of the resonator. And a consequence of that is if you measure the resonator when the qubit's in 0, you'll tend to get a point near this blue cloud on the left. And if you measure when the qubit is in 1, you'll tend to get a point near the red cloud on the right. And so when we do any individual measurement, we can basically draw this line in the sand here and say if we are on the left side, we are going to call that a 0. And if we're on the right side, we're going to call that a 1. One more subject like this I want to describe is how we get entanglement in our devices. And the particular gate I'll focus on is the controlled phase or CZ gate. And the way that we make this is we basically take two transmon qubits. If you put them next to each other, there's a capacitance between them that allows them to swap photons with each other. And actually, we use a special circuit to tune the coupling between them so we can turn it on and off at will. But let's not worry about that for the sake of this discussion. So for the CZ gate in particular, we're going to arrange the frequencies so that the 1-1 state, that is each qubit has one photon, has the same frequency as the 0-2 state, where the higher frequency qubit has two photons. And this capacitive coupling brings about an I swap kind of interaction, so that 1-1 will turn into I times 0-2, and then that will turn into minus 1-1. Whereas the other computational states like 0-1 and so forth are not affected. And so that's why it's a conditional phase on just the 1-1 state. And this is equivalent to a C0 gate up to a couple of simple local qubit gates. We can also do a wide variety of similar gates, but in this presentation, we're just going to focus on the control Z gate. And it's not just about the qubits. If you have the qubits, you also need a bunch of support in order to actually make them work. So we have, for example, you put them in a circuit board, in a package, you mount that package in a dilution refrigerator that can cool down to around 10 millikelvin. Then the package is connected to all of these cables. Those go to various filters and amplifiers and so forth up through this fridge. They then connect to electronics, which is then controlled by software and so forth. And as you can tell, there's a lot of stuff that goes into actually making one of these experiments work. But I'll leave it at that for the sake of this presentation. So this concludes my discussion of how qubits work, how our devices actually work. And what I want to do now is go to a couple of recent publications from our group. And this first one is about topological quantum states. And I wanted to highlight that this is the product of a great collaboration between the whole Google team and then also some external collaborators at TU Munich, Yuji Liu, Adam Smith, Michael Knapp, and Frank Pullman, and then also from Caltech during her postdoc, Christina Knapp. And what we're going to study in this part of the presentation is the Kitaev toric code, which is an instant classic 2D lattice model. So we're concerned with this Hamiltonian, which is a sum of local parity operators on qubits on a two-dimensional array. And you can see in the upper right this diagram showing where the qubits live. They're the circles, and they live on the bonds of a square lattice. And then these local parities are the star operators, which are parities like Z, 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 Z around a vertex in this array. And then the operators B are the plaquettes, and they're operators like X, 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 X around the faces of one of these squares. And these operators are pretty cool because even though X and Z don't commute on the same qubit, since these will overlap on an even number of qubit, all of these star and plaquette operators commute with each other. So they can be simultaneously diagonalized. And hence, the ground state of this Hamiltonian is going to have a +1 eigenvalue on all of these local parities. Now, such a state has a lot of interesting properties. They have long-range entanglement, which we'll explore a bit more. The excitations in this model are anyons. There are applications in quantum computing, in quantum error correction, as we'll get to. And the degeneracy of this Hamiltonian depends on the boundary conditions. It's called the toric code because it was originally conceived of with periodic boundary conditions in space, so on the surface of a torus. But I don't have a torus, so really we're just going to be focusing on two-dimensional non-periodic boundary conditions. You might think of this more like the surface code, but this Hamiltonian is associated with this phrase toric code, so that's why I'm going to use that. One more thing. This diagram in the lower right is a stained glass plot. This is just a way of visualizing expectation values of parities. So we have a tile for each of these star and plaquette operators, and then the color of that tile will show a parity value, as we'll see. Now, let's understand the ground state using a simple example. And here we're just going to look at a 12-qubit example with these boundary conditions, blue boundary conditions all around. And I'll tell you, in this case, there is a unique ground state where all of these parities are +1. And let's just understand how that state works. So if you start with all of the qubits in 0, this is already a +1 eigenstate of all of the Z parities. But it is not an eigenstate of any of the X parities. So what we're going to do is sequentially project this state so that it is an eigenstate of each of the X parities by applying an operator like I plus XXXX. And this kind of doubles the superposition that we have each time we apply one of these things. And there are 4 of them here. You'll also notice, for example, as these XXXX operators get applied to adjacent plaquettes, we have these cancellations, which result in kind of loops of ones around the dark purple squares here. Now, inspecting this state a little bit more closely, you can see that each of these 16 bit strings satisfies all of the Z parities, and they still do because the Z and X parities commute with each other, so projecting into an X parity eigenstate doesn't affect the Z parity. Meanwhile, the superposition of all 16 is an eigenstate of each of the X parities. And the way you can think of that is if you applied one of these operators, XXXX, it basically shuffles around these 16 bit strings, but you still have the same superposition of 16 bit strings. And now that we understand the ground state, we can come up with a plan to actually make it. Because in this project, we're going to create eigenstates of the toric code model using quantum gates. We're not actually going to have the Hamiltonian exist in real life. And so our plan to make this state in real life will be, first of all, we're going to assign kind of a team captain qubit to each of these X plaquettes. And then we'll do a Hadamard on each of those team captains. This will create a superposition of the 2 to the 4 states that we see here, but without the entanglement that we need. So the final step is to do a controlled knot between each team captain and its 3 teammates, bearing in mind that one of its teammates might themselves be a team captain. So we have to be careful how we arrange this. And by doing all of those control knot gates, we kind of stitch entanglement across the array in order to land on the state that I have listed here. Let's see what that algorithm looks like in practice. So here we're looking at a 31 qubit system, which is the system we'll be studying for most of this part of the presentation, this nice 2D array of 31 qubits. And in these diagrams, what I've displayed is kind of an operation like a set of quantum gates, or we're starting with all the qubits in the 0 state, for example. And then under that, I have plotted this stained glass plot where we have all of the Z and X parity expectation values, which we can experimentally measure after that step has occurred. So we start out with all the qubits in 0, and you can see all the blue tiles there. That's because this is already a +1 eigenstate of all the Z parities, but not any of the X parities. Then we'll do a Hadamard on each of these 12 team captain qubits, and this creates a non-entangled superposition of 2 to the 12 states, about 4,000 different bit strings. Then the job of these successive layers of simultaneous C0 gates, which are again created using our CZ gates, is to stitch this entanglement across the device. And we start in the center and then work our way out from there. And when we get to the end, we've been able to make all of these parity values +1, both the blue and purple, both the Z and X parities. And taking a closer look at these parity values, we can see that they're all close to +1 as desired. And the values are a little bit further off in the center of the device, which we can understand because the center of the device is where we first created the entanglement, and then those qubits had to kind of wait around while we finished the algorithm working our way outward. But I think it's fair to say that this is a good realization of a toric code eigenstate. And let's see what we can do to explore its properties. Now, I mentioned that a great property in the toric code model is that the eigenstates exhibit long-range entanglement. And this is a rather subtle concept, but it turns out that there's a nice quantity called the topological entanglement entropy, which is a signature of this long-range entanglement. Now, if we look at a given subset of our device, like this 3x3 lattice embedded inside the larger 31 qubit lattice, the entanglement entropy of that is measuring the entanglement between that subsystem and the rest of the device. And in this case, there will be 2 contributions to that. One is associated with the perimeter going around it, and one is associated with this long-range entanglement that's going to be a constant for any subsystem size. And it turns out that if we want to figure out what this topological entanglement entropy is, what we need to do is look at several different slices of this same subsystem and their entropies. And if we cleverly add and subtract these different subsets, we can make all those boundary contributions cancel out and just be left with the topological entanglement entropy. Another great property of the toric code model is all these entanglement entropies are supposed to come in integer multiples of log 2. So this is a great way to explore, now that we can create the state, we can explore ways to measure entropies in non-trivial entangled states. And we know exactly what the correct answers are supposed to be, so we can explore different methods. For example, measuring the entropy of this 9-qubit subsystem is pretty tricky, and you'll have to check out the paper for more information about how we managed to pull that off. But in summary, we can look at these entanglement entropy, these topological entanglement entropy values for different sizes of subsystem as we scan them across the device in order to get these distributions, and we observe values that are close to the expected value of minus log 2, that is kind of the direct measurement of this long-range entanglement that exists within this state. Another very interesting property in the toric code model is its excited states. And I have excited in quotes here because we don't actually have the Hamiltonian in real life. It's kind of all in our heads. But it's easy, once we have an eigenstate of the toric code Hamiltonian, to transform between different eigenstates simply by applying x and z gates on individual qubits, which is very easy to do. So for example, on the right, we have a case where we started with the ground state and we applied a couple of x gates here, and these x gates flip the z parities. So that's why we see these blue tiles have turned red, and we've labeled those E. And over on the right side, you can see how these z gates have flipped one of the x parities yellow. And these -1 parity values in the toric code model are associated with excitations. E and M are anyons, and then psi is E and M considered together, which is a composite fermion. These -1 parities are also closely related to quantum error correction and the detection of errors. You can see how like tossing an X gate into here will cause some of these parities to light up, and we'll explore that a bit more later. But something else we can do that's kind of cool while we're here is we can make a movie where we sequentially create these various eigenstates, where we kind of move this red tile around its neighbor, the yellow tile. Now, we happen to know in the toric code model that if you move this red tile around the yellow tile, that operation, even though you brought it back to where it came, actually changes the state. It puts a phase of -1 on the state. And it would be very cool if we could actually measure that, because of course, measuring a global phase is kind of a tricky proposition. And so we're going to do this using a simulation of braiding statistics. And the trick is to bring in an extra qubit, this green auxiliary qubit. And its job is to measure expectation values of operators like U, that's that loop of X gates, for example, any loop of poly gates, and phi, which is a particular toric code eigenstate that we're paying attention to. And the basic idea is we start with the green qubit in the plus state, and then we do a controlled U operation onto qubits that are in phi. And this actually maps the eigenvalue e to the I theta onto the green qubit, where then we can measure it. We can measure it by way of its phase using single qubit tomography. And one way to think about why the controlled U operation is important here is it's like we start out in the superposition state 0 phi plus 1 phi. And then the controlled U operation sort of doesn't do anything to the 0 phi state, whereas it applies the operator U to the 1 phi state. And so we get that eigenvalue there, which then if you refactor this, you can see that this is on the phase of the green qubit, and so we can measure it. For example, let's look at the bottom of the slide here. These are again experimentally measured parities where we have a particular toric code eigenstate that we want to check out. And let's see what the expectation value of XXXX is. And you can think of that operator as kind of moving that upper right red tile around the yellow tile that's next to it. And after performing this controlled XXXX operation, we can then again measure the parities, and we see we still have the same state here, but you can see fading in the colors in these parities, which is due to things like gate error and decoherence and so forth. But nonetheless, we still have the same eigenstate, and the phase associated with this XXXX operator has now been mapped onto the phase of the green qubit, which we can measure. By the way, this operator controlled XXXX is a pretty non-trivial, non-local operation. And the way that we do it is by compiling it into Control-Z gates. The basic idea is that we take the state of the green qubit, swap it into the array, and then as we swap it back out of the array, we perform C-naughts along the way. So it's kind of like a sewing machine, and that way we can implement that operation. Now we can do this for a wide variety of different operators and eigenstates in order to cover all of the different combinations in the toric code model of mutual and exchange statistics. And these are just all the data sets plotted here. And then the phases that we measure are plotted on the right. And we measure close to what we expect for the toric code. These are, of course, very well understood exactly what phases we're expecting to get, where these 5 are close to 0. And then these 4 are close to pi. And it's very cool that we're able to actually measure this. And then there's a natural extension where hopefully in the future we can use similar techniques to explore more interesting and novel models in order to figure out their braiding statistics. But that's enough about that. What I wanted to close this part of the presentation on is something that I'm really enthusiastic about, which is logical qubits. And the name of the game here is a ground state degeneracy. Now, previously, we were looking at cases where we had these blue boundaries all the way around. And in those cases, we had a unique ground state. But by changing the boundary conditions, we can create a degeneracy. And those degenerate states have a very important property, which is they're locally indistinguishable, which is going to be very useful for the logical qubit, as we'll see. So in this case, we change the boundary conditions so that we have blue boundaries on the sides and purple boundaries on the top and bottom. And having done this, we can introduce a couple of new operators. So in addition to the local parities, we have kind of these global parity operators, the Z and X logical operators, which span from one side of the array over to the other side. And these operators commute with all of the local parities and hence with the Hamiltonian, so they can be simultaneously diagonalized. But they anti-commute with each other, just like Z and X for a single qubit anti-commute with each other. And so using a similar circuit to what I had described earlier, but adjusted for these different boundary conditions, we can create states in this logical qubit space that have a +1 eigenvalue on all of the local parities. But you have to make a choice of which state in that space you want to create. For example, you could say, I want Z logical to be +1, and then you're creating the state 0 logical. And I'll mention that these plots on the left here are, again, experimentally measured parity values after we've created these logical qubit states using a similar circuit to what I described earlier. Having created these states, a natural thing to want to do is a logical measurement on the states. And so suppose you want to measure the logical qubit in the Z basis, then what we're going to do is measure all of the physical qubits individually in the Z basis. And then you could immediately evaluate this value of the parity Z logical, like Z, 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 Z across the device. But that would be leaving something on the table, because when we created this state, we designed it to have all of these parities, these local parity values, be +1. And so with these measured bits, we can actually calculate each of those local parities, the Z parities. And we can see that in some cases, some of them are not +1, they're actually -1, which are these red squares here. And those -1 parity values are signaling to us that there was some kind of error nearby. So what we can do is try to fix that error by finding a minimal set of qubits to flip such that we basically turn the red squares back to blue and make all of the parities +1. And in some cases, such as the example here, this actually flips the value of the logical operator. And so we are correcting an error. We're preventing a logical error by doing this correction process. And you can do something very similar in the X basis as shown at the bottom here. Here's another one that I'm not going to cover in great depth in this presentation, which is that we can create arbitrary logical superposition states like alpha 0 logical plus beta 1 logical anywhere on the logical block sphere that we want. And the basic way that this works is you take the middle qubit and you initialize it in the state alpha 0 plus beta 1 that you desire. And then we use a similar circuit to kind of spread out that state and stitch it across the whole device so that we land in this logical superposition state that we desire. Once you've created that state, we can then find a point on this logical block sphere by doing logical tomography. So we can measure Z logical, we can measure X logical, like I was just describing. We also want to measure Y logical. It's actually a little tricky to do that, but you can check out the paper to see how we actually did that. And what you can see in this data on the left is on this logical block sphere, we can basically fill it in anywhere we want to go on that sphere. But that's the logical information. Something I mentioned earlier was that this logical information is invisible to the local parities. They're locally indistinguishable. And one way we can visualize that is by looking at these local parity values for several different states that look very different when we do the logical tomography. But if we just look at the local parities, 0 logical, 1 logical, the T state, all of these states really look the same. And that's closely related to why they're kind of immune to local errors, or why we can fix local errors, and why they make good logical qubits. One more thing here. Let's explore logical decoherence. And what we're going to do is create a particular logical state. Here, let's focus on 1 logical in red and plus logical in purple. And then we're going to let it sit around for a period of time and then measure it, do the logical measurement, and see what fraction of the time we make a logical mistake. The first lesson we can take here is that the correction helps a lot, comparing the raw measurements to the corrected measurements, and it actually helps more for the distance 5 case. After the correction, distance 3 and distance 5 perform similarly. It's actually one's better in each basis, and I think that's just down to inhomogeneities and individual errors across the device. But we expect that if performance were better overall, if all our individual components had better performance, then the distance 5 would overall perform better. Something else you can notice in the corrected data is that the plus logical has its error still increase much more rapidly than the 1 logical case. And that's because this state is more vulnerable to dephasing. And we can mitigate a lot of that dephasing using a simple dynamical decoupling protocol where we do a couple of X gates spread out during this wait time. And this basically echoes out or cancels out low frequency noise that's responsible for the bulk of this dephasing. And having done that dynamical decoupling, we're then down with the solid purple symbols at the bottom, and you can see similar performance between 1 logical and plus logical. But as you can see, over the course of these hundreds of nanoseconds, logical error starts to pile up, and it's not going to go down. So what would be really nice would be if we could over and over again projectively measure each of these local parity operators, and that would signal to us where errors happen. We would be able to fix them and preserve the logical information indefinitely. Now, that's not possible here, but it is something that we consider as we close out this section and move on to the final part of my presentation, which is discussing catching errors with repetitive measurement. And so if we return to our distance 5 logical qubit, but we now reinsert these green measure qubits, these 24 green measure qubits, each of them is responsible for measuring over and over again these local parity operators. And by doing so, we'll be able to detect if any errors happen on the device. And then we can take them into account and try to preserve the logical information over a longer period of time. Let's look at a small example of how this works, how this projective measurement of stabilizers works. Let's consider just 2 data qubits in blue here, where we want to projectively measure ZZ and XX. And you'll notice that those 2 operators commute with each other, so we can simultaneously diagonalize them. And their mutual eigenstates are the Bell states. And in this case, if we put any 2-qubit state into this circuit, and then we measure XX using this circuit, you'll notice this is very similar to the simulating braiding circuits where we're projectively measuring these operator expectation values. Very much the same. So we do a projection onto an XX eigenstate, then we do a projection onto a ZZ eigenstate. Each of those kind of cuts the Hilbert space dimension in half, and you're left with just one state that satisfies both of those, and it's going to be a particular Bell state. For example, it might be 0, 0 plus 1, 1. And in that case, both of the stabilizers would be plus 1. But let's consider what happens when we toss an error into this circuit, some unwanted operation like this red Z gate here. So that's going to flip the phase of this superposition. So now it's 0, 0 minus 1, 1. And now when we measure this operator XX, it's going to show up as -1 instead of +1. And that allows us to detect that a Z error has happened, whereas the ZZ still shows up as +1 as expected. And what this tells us is an error happened and we now know which state we're in. And it works not just for a discrete Z operation, but it also works for a continuous operation. So consider a small continuous rotation Z to the epsilon. After we do that, we're in this state with a small phase on the 1,1 state. So now when we measure XX, the outcome is actually probabilistic. With large probability, we'll probably project back onto 0, 0 plus 1, 1 with XX equals +1. And it's like this error never happened. But with a small probability around epsilon squared, we'll actually project to a discrete error and we have 0, 0 minus 1, 1. So it's like a discrete Z error occurred. And this projection of continuous errors onto probabilities of discrete errors is a really core concept in how the surface code and these stabilizers actually work. But this is just 2 qubits, it's a Bell state, we don't have a logical qubit. So let's explore a very small logical qubit, which is the distance 2 surface code logical qubit. And here we have 4 data qubits, 2 by 2 grid, and 3 measure qubits. So we start out with a Hilbert space dimension of 2 to the 4, and as we do these 3 projective measurements, we're left with a Hilbert space dimension of 2. And that is where our logical qubit lives. We can do experiments with this where we actually make this happen in real life. We measure these stabilizers over and over again and figure out what logical errors we get at distance 2. I'm not going to go into great depth on this in this presentation, but you can check out our paper. And also at the bottom, you can see quite a few different groups have done experiments with these distance 2 logical qubits that you can check out. But one nuance of this particular small code is that since it's so small, it can detect any single error, but it can't necessarily discern its logical effect. And so if we want to evaluate the logical error we get at each round, what we'll do in practice is discard the rounds where any error was detected. And that's what this left plot is. As we increase the number of rounds, the fraction of rounds where no errors were detected decreases exponentially. And then in the right, if we just consider among those rounds where no errors were detected, how often do we see a logical error? And you can see that that also increases as we go through more rounds. And then we can compare our data to models, we can make error budgets and projections and so forth, but you'll have to check out our paper for more details on that. Another subject to cover here is the repetition code. And this is a tool that we use to test the scaling behavior of these error correcting codes with existing devices. And the repetition code is closely related to the surface code, but it's like a one-dimensional version of it. And it's much easier. The error threshold is much easier to achieve. And since it's one-dimensional, we can kind of snake it around our device and thus test larger distances. However, it's not a fully protected logical qubit. So it's just a way to test kind of the infrastructure and the basics of running these stabilizers and doing error correction. Now we actually test this out, and as we explore from a smaller code of 5 qubits going up to a larger code of 21 qubits, as you increase that code size, you're dramatically reducing the logical error that we experience. And it's clear in the log scale, since these are evenly spaced, that we have this exponential suppression of logical error that we hope for and expect for an experiment like this. In fact, it's a factor of 100 going from our smallest system to the largest system here. So that's very promising. And there's one more subject, kind of a detail that I want to cover here, which is back to leakage. So this is a subject I mentioned at the beginning, talking about transmons, how we're using the lowest 2 energy levels as our qubit states. And there are higher energy levels, and we can accidentally populate those higher energy levels, and that's called leakage. In particular here, let's check out the 2-state population. This is the just right above 0 and 1, the 2-state leaked state. If we run a repetition code for many rounds and we measure after each round if any of the qubits have leaked, we can see that this increases over time. This is this red data in the left plot here. And this is a problem. Leakage is a really big problem in quantum error correction. It's hard to deal with, and we really want to try to mitigate it in hardware instead, because it can cause these long correlated errors across the device over space and time that are really tough to correct. So let's use a multi-level reset routine in order to dump all of the energy out of our measure qubits each time they're measured. And this way we're kind of starting with a fresh slate on each round. And the way that we're going to do this is to pass this measure qubit by its readout resonator in a careful way so that we swap its energy into the measurement resonator. Then we wait for that energy to decay out through its transmission line. And then once that's done, we can bring the measure qubit back up to its operating frequency, and it can go about its business of doing the next round of error correction. And this whole thing takes a couple hundred nanoseconds, which is pretty fast, but it's still a significant amount of time. And what's really cool about this is that not only does it reduce the leakage, so in this plot on the left, we can revisit it and see the blue points where we have included this leakage protocol. And now not only do the measure qubits have really bottomed out leakage, even the data qubits have significantly lower leakage, and it saturates faster to a smaller level. And that's because leakage can kind of move around on the device. And so the measure qubits are still helping decrease the amount of leakage on the data qubits. Not only does it help with the leakage directly, but by getting rid of that leakage, we improve the logical performance significantly because the error correction problem is much easier. So even though we're adding a couple hundred nanoseconds of runtime to each cycle here, we have a significant improvement in the logical error with the reset installed. So this is a really cool result here, and it's something to continue to explore to try to get rid of leakage in quantum error correcting codes. But that about wraps it up here. So this is a brief description of our recent paper. For more detail, you'll really want to check out the paper where we're looking at these repetitive measurements of stabilizers, and in particular, the exponential suppression of error in a repetition code. And so let me wrap up. In this presentation, I described our overall plans to build a large error-corrected quantum computer. Then we zoomed in to talk a little bit about how our qubits work. And finally, talked about two recent papers about topological quantum states and repetitive error correction. So let me just close here and say thank you all so much for watching, and I hope you have a great day.